So in studying momentum, we learned that momentum is the product of mass times velocity. So when two objects interact with each other and there is a force on one object due to the other, so an object 1 pushes on 2 and object 2 pushes on 1, Newton's third law tells us that for every force there is an equal but opposite direction, equal magnitude force between two bodies. Now, if this is the net force acting on each one of these objects, meaning that only this vector is causing a change in the motion of object 1, and only this force is changing the motion of object 2, then we can say that this is the net force on 1 is equal but opposite in direction, equal in magnitude, opposite in direction to the force on the other object. Now, if you remember, our net force is equal to m times a. So in this case, this would be mass 1 times A1, and that will equal negative mass 2 times A2. So now when we look at what does acceleration mean, remember acceleration is the change in velocity over a change in time. So that means that A1, the acceleration of object 1, would be the final velocity of object 1 minus the initial velocity of object 1 divided by the change in time, so the final time minus the initial time. Now, when these two objects interact with each other, let's say that the initial time, so t initial, is 0. And so now when we look at substituting in for m times a, we'll have that mass 1 times velocity 1 final minus velocity 1 initial over, this will be t final, is equal to negative, don't forget this negative sign up here, that's important, and then that will be equal to, so m2, and we're going to do the same thing for a sub 2, our acceleration of the second object, but this time this will be velocity of object 2 final minus the velocity of object 2 initial divided by t final. Now these objects are in contact with each other for the same amount of time. 1 can't touch 2 for a different amount of time than 2 touches 1. So that means that t final is equal to t final. And so we can multiply by t final on both sides of this equation, and we'll have a simplified result of mass 1 times v1 final minus v1 initial, which is equal to negative mass 2 times v2 final minus v2 initial. So let's distribute our mass. So this would be m1 v1 final minus m1 v1 initial is equal to negative m2 v2 final plus, remember distribute the negative sign in there, plus m2 v2 initial. And notice that I have final conditions on both sides and initial conditions on both sides. So let's rearrange this so that we have our final conditions on one side and our initial conditions on the other side. So then, so that I'm going to leave the final conditions on the left side, so that will be m1 v1 final, and then I'm going to add this over, and so plus M2 V2 final. I'm going to leave the M2 V2 initial on the right side and add over M1 V1 initial. So now I have my initial conditions together and my final conditions together. And this right here, mass times velocity, is momentum. So this is the final momentum of object 1. And this is the final momentum of object 2. And this is the initial momentum of object 2. And this is the initial momentum of object 1. And on both sides I see that these quantities of momentum are added together. And whenever something's added together, that means we have a sum. Remember, sigma means sum. So the sum of the final momenta of the system of two objects is equal to the sum of the initial momenta of the system. And when you have a final condition equal to an initial condition, and there's no change between the final and the initial, we call that a conservation. And in this case, since that conservation is applied to momentum, this is the conservation of momentum. Now, momentum is always conserved in collisions and interactions as long as there are no external forces acting on the system. So that means if we look back at our picture earlier, when these two objects were sitting on this table and they were moving towards each other, and there was a collision that caused them to, and they struck each other, such that 1 was pushing on 2 and 2 pushed on 1. Those were the only two forces on the objects, the system of our object 1 and our object 2. Just the force from 1 onto 2 and the force of 2 on 1. Those were the only forces acting. So there were no external forces acting on our system of two objects. So the conservation of momentum can be very simply written as this expression here, that your final momentum is equal to your initial momentum. But this version of the equation is a little more useful because we will know the initial velocities and masses and be able to determine the final velocity and mass. And we use the conservation of momentum often when we're determining who was at fault for an accident, or possibly the ballistics reports on crime scenes when firearms are used. Those are all cases in which, if we know the mass of the object and where the object is located after the collision, we can determine the initial position, the initial speed, and determine many pieces of the puzzle to see who was at fault. So let's look at the types of collisions. There are really two main types of collisions, and one type has like a special little condition for a third type of collision. So there is first a collision that we call inelastic. So the prefix in, like incapable, that means not, and the word elastic is a word that indicates energy. So in this type of collision, energy is not conserved. However, momentum is. Momentum is always conserved in all of our collisions. There's a special subset of inelastic collisions. This subset is called perfectly or totally or completely inelastic. This collision is special because they stick together. And then the opposite of the perfectly, totally, or completely inelastic collision is a recoil or explosion. Mainly, the important part is that the object is together to begin with, and then it breaks apart. So when we define the conservation of momentum for these collisions where they stick together or these explosions where they break apart, we can write our conservation of momentum equation a special way. So we'd have m1v1 initial plus m2v2 initial is equal to the combined stuck together m1 and m2 are now together, and they have a common velocity that I like to call v3 because it's not 1 or 2, but it is the velocity of 1 and 2 together. Similar, when we have a recoil or an explosion, the system is together to begin with. So the initial momentum can be written as m1 plus m2 times v initial, because it's just the initial velocity of that system. And then they explode, and m1 will have a v1 final, and m2 will have a v2 final. Second type of collision is an elastic collision. This is one in which energy is conserved. And of course, momentum is also conserved. What's important here is that both the sum of the kinetic energy initial is equal to the sum of the kinetic energy final, and the sum of the initial momentum is equal to the sum of the final momentum of the system. And remember, our kinetic energy is 1/2 mv squared. So we would have to find the kinetic energy of each object before and after the collision. Now, that can be a pretty long equation where you'd have m1 v1 initial plus 1/2 m2 v2 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And then for our conservation of momentum, I'll come down here. So this is our conservation of energy. So our conservation of momentum will look like m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. So these two equations can be used together to solve problems. Now, the problem that you'll run into is that this can be pretty difficult algebraically to deal with. So if we mathematically reduce these two equations, we can get a third equation, a special equation to use, and it looks like this, that v1 initial plus v1 final is equal to v2 initial plus v2 final. This is a very special equation that only works for elastic collisions. So this is for elastic collisions only.